Albert Einstein and Aristotle had one important idea in common: the stability of the universe. Now, Isaac Newton was a Christian. He thought that the universe had a beginning with its creation by God and that it would have an end in accord with the prophecies of the books of Daniel and Revelations. But Aristotle and Einstein held the opposite view: that stability is the essence of reality, that the universe is as it always was and always would be. The universe is a functional system governed by laws of nature that would have always been and always will be in place. The way things look now is just how things are. For Aristotle, this meant the complex interplay of circular orbits could be wound as far forward or backwards as you would like, and it would look invariably the same. For Einstein, the field equations of his general theory of relativity gave us an understanding of the relation between space-time and the mass and energy in it. That relation could also be fast-forward or rewound to any time and seem substantially identical. This belief would lead to what Einstein called his greatest mistake. Correcting that mistake led to a complete redefinition of reality, forced us to see the universe differently. In 1917, the year after he published his general theory of relativity, Einstein began to consider what the theory meant for cosmology, the large-scale study of the structure of the universe itself. To his horror, Einstein came to the realization that the results of his theory were not stable. The picture of the universe that the solutions of his equations gave him had space-time always expanding or contracting. Now, he visited a colleague, the Dutch physicist Willem de Sitter. The two worked hard, producing two possible approaches that would restore stability. De Sitter's approach to stability would only work if there was no mass in the universe. Adding even two tiny bits of mass would cause them to shoot off from each other at great speeds. That wouldn't work. Einstein's own solution showed that if there was an infinite number of stars in space, then the stars would be moving at absurdly fast speeds, something we don't see. And if there were a finite number of stars, then the universe would be expanding or contracting. That wasn't acceptable either. Einstein's theory says that the presence of mass and energy causes space-time to curve. The universe, Einstein argues, is like the Earth. When you look up close, there are mountains and valleys, flat plains and hills, but when you pull back and look in the large, it's a smoothly rounded surface. In the same way, Einstein thought, there would be local bumps in the curvature of space-time, but in the large, from the cosmological perspective, the universe had to have a smooth and constant curvature. The only way to get this smoothness and not have the universe expanding or contracting was to add a term to his equations, what came to be known as the cosmological constant. Now, there was nothing in the physics that demanded this term. There was nothing in the observations that demanded this term. It was only required to make sure that the picture of reality as regular could be maintained. Younger, cleverer physicists objected. The Russian Alexander Friedmann produced a solution to Einstein's equation that showed an expanding universe. Einstein first told Friedmann that he had made a mistake. Then, realizing Friedmann's work was error-free, argued that, yes, it is a solution, but that it wasn't one that described our reality. Georges Lemaitre, a Belgian physicist and Catholic priest, also found the general theory of relativity to require an expanding universe. Again, Einstein refused to accept it. When Lemaitre presented his findings to Einstein himself while the two were riding in a cab, Einstein famously remarked to him, "Your calculations are correct, but your physics is abominable." The idea that there were large-scale changes happening in the universe violated the paradigm, the basic idea that we live in a stable universe. But in 1929, the universe told us otherwise. Edwin Hubble, working on the newly built telescope at the Mount Wilson Observatory in California, observed something amazing. Now, the instrument on Mount Wilson was the largest in the world at the time, and was used to observe the first objects outside the Milky Way ever seen by human eyes. This, in and of itself, was incredible. There were other galaxies out there. By itself, this expanded the size of the known objects in the universe by 100 times. But it got more interesting when Hubble documented how far away they were and how fast they were moving. Turns out the farther away they were, the faster they were moving, and the more likely they were to be moving away from us. From these facts, Hubble concluded that the universe is expanding. So, how does he get there? First, galaxies are made of stars. We know that they shine, and the light they give off is a result of their chemical composition. Right? All stars work according to the same mechanisms. Right? They turn hydrogen into helium. Now, each element has a fingerprint, a set of telltale frequencies of light that they give off because of the structure of the atoms. As a result, the light from all stars and all galaxies should look the same. But light is subject to the Doppler effect, a phenomenon we're more familiar with in terms of sound. Think about what it sounds like when an ambulance with its sirens wailing drives past you. As the ambulance approaches, the tone of the siren gets higher. As it drives away, it gets lower. The siren is giving off sound waves, and the pitch of the sound is determined by the frequency. That is, how often, how frequently, the peaks of the wave pass you. As the ambulance moves towards you, the waves emitted by the siren get a boost from the fact that the siren is moving towards you. That boost means more peaks pass in a given second, and that means the frequency, and thus the tone goes up. As the ambulance drives away, the speed of the wave is decreased. It takes longer for each peak to pass you, and so it happens less frequently. Thus the tone goes down. The faster the ambulance is going, the more notable the shift in pitch. Same thing happens with light. The light wave is moving at the same speed no matter the state of motion of the light source. Remember, that must be true from the theory of special relativity, but the number of peaks per second changes based on the relative motion of the light source. If the light source is moving towards you, you get more peaks per second and the light will shift towards the blue end of the spectrum. If it's moving away, you see fewer peaks per second and the light will shift towards the red end. The amount of red shift or blue shift tells us how fast something is moving and whether it's moving towards or away from us. For the astronomer, it's a great tool. Now, Hubble noticed something weird. The farther away something is, the more likely it is to be moving faster and moving away. Very few objects are blue shifted, that is, moving towards us, and those tend to be objects that are among the closest. From this, he inferred that the universe is expanding. To see how he gets there, the usual model is raisin bread. Now, to make raisin bread, you take a bowl, add some flour, salt, sugar, yeast, water or milk, and most importantly, raisins. Mix them together to form a dough, knead it well, and let it sit so that the dough will rise. Now, when you first put the bowl aside, the raisins are fairly evenly distributed through the dough. Over time, as the dough expands, the average distance between raisins increases also. The raisins spread out with the rising dough. Now, pick a raisin and try to think about what the process looks like from its vantage point. At first, it's in a small neighborhood surrounded closely by other raisins. As the dough rises, it's taken along its own direction like all other raisins. What were once small distances between it and neighboring raisins increase as every raisin isn't following a path like this raisin as it moves out during the expansion. A few raisins will be close by and getting pulled along similar trajectories as the dough rises, but the overwhelming number of raisins will be moving away. Not only that, but the farther away a raisin was to start, the farther away it ends up in the end. Neighboring raisins will separate, but only by a bit. Distant raisins will become even more distant. Since time is fixed, that means it moved farther in a given time. In other words, it was moving faster when judged from the perspective of our chosen raisin. In an expanding space, like raisin bread, most stars and galaxies will be moving away, and the farther something is, the more likely it is to be moving away and moving faster. That's what Hubble saw in the telescope and how he could conclude that his experimental findings were exactly what was predicted by Lemaitre's theoretical account of an expanding universe. When we say that the universe is expanding. We mean that space-time itself is expanding, not that the things in it are moving away from each other in a fixed space. It's not that the universe is an island of mass taking up more space as time goes. It's that the universe itself, space-time itself, is expanding. What's it expanding into? Nothing. It's not a thing in space or a surface in space taking up more room. It's the space itself that's expanding. Doesn't that mean that there's an edge, a limit, and that it's increasing? No. It doesn't mean that the universe is bounded. Now, this is often difficult for people to visualize. So let's think of a television set. When you're young, everybody's mom told them, don't sit too close to the television set. It'll hurt your eyes. But we all did it. And what did you see when you sat very close to the TV? Dots. Pixels that turn colors. And this is amusing for a while, but it's generally more entertaining to watch them in bunches because the pixels work together to form images of things and people. Now, suppose we have not only a big screen TV, but an infinite screen TV. Now, what does that mean? It means that no matter what pixel you take, there's a pixel to its left, a pixel to its right, a pixel above, and a pixel below, right? There will be no edge pixels. No matter how far you look in a direction, there are pixels out there and ones next to them and next to them and next to them and so on. So it's an infinite screen TV. Now, your dad comes home with it, installs it in the living room. Your mom tells you not to get too close to the infinite screen TV. But we know how well you listen. You put your nose right up to the screen and what do you see? Pixels. But what's happening is that every so often, the pixels you see spread apart and new pixels appear between the old one in every direction. You pick a pixel. There's a pixel above, a pixel below, to the left and the right, right? After a second, those pixels are still above, below, and to the left and right, but now they're 2 pixels away from the central pixel you were watching. In this way, what we see on the screen is expanding. The things on the screen are not expanding. If you step back, the images you're looking at still take the same number of pixels to be shown. It's still the same size. But because there are more pixels on the screen there, it's farther away from other images on the screen than it was close to. But while there's expansion on the screen itself is not expanding. It was infinite before, and it's infinite now. Take any pixel, and there's another pixel next door in each direction. We have expansion of space without having a bounded space that's expanding into something larger. The screen is expanding while remaining the same size. That's what's happening in the universe. It's expanding, but that doesn't mean it's bounded or embedded in something larger. But if it's expanding now, that must mean that it was more compact previously. What's causing the expansion? That was the central question in cosmology following Einstein's general theory of relativity and Hubble's discovery of the expansion of the universe. 2 theories arose. One came from the Aristotelian Einsteinian static universe picture, and one challenged it. The challenger, of course, is what we now call the Big Bang theory. This is not the name that the scientists who worked on it proposed. They preferred primordial nucleosynthesis. The term Big Bang was coined by Fred Hoyle, an opponent of the theory, and was designed to denigrate it. The central idea is that if the universe is expanding now, it must have been compressed before. If it's getting bigger, it used to be smaller. But if it's getting bigger, something must be causing the expansion. There seem to be 2 possibilities. Either a constant force that's always at work repelling things, or an initial event that caused the expansion. And what we're seeing are the lasting effects of that force. The first one seemed to have the problem that the only effective force operative over long distances is gravitation, and gravitation is an attractive force. So we're left with the second possibility. There was some singular event that happened at the beginning, and we're still seeing the results of it everywhere, even now. Scientists hated this idea. First of all, we don't see this sort of event regularly and have never seen versions of it under laboratory conditions. Why should we think such a thing happened? Unique events seem utterly unscientific. To claim that we can rewind the film to a point where all mass and energy is concentrated at a single point only to explode into a universe like ours is tantamount to theology. It's positing a creation event that grossly outruns what we can infer from the fact that the galaxies are moving away from each other. If you want to say there was a Big Bang that brought our universe into its current state at some point in the past, well, what caused it? And what happened before that? These are questions for which there could not even possibly be empirical answers. They aren't scientific questions. The Big Bang theory itself thus seemed like fantasy, not real scientific work. There were scientific advantages for a Big Bang theory. If it were true, then it would offer a solution to a problem called Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers. Problem's simple. Proposition 1, space is big, really big. Proposition 2, there are lots of stars out there, lots and lots of stars. So, putting 1 and 2 together, if you point to any spot in the sky and travel in that direction far enough, you'll eventually hit a star. Proposition 3, stars shine. That is, they emit light, right? That's what we see up in the sky. Now, putting 1, 2, and 3 together, if every point in the sky leads to a star, and the light of that star is visible in the night sky, then the entire night sky ought to be glowing. It should be as bright in the night as it is in the day. So why is night dark? Big Bang theory gives us a nice, easy answer. The universe is of a finite age. It might be true that there's a star along any line you point out, but it takes an amount of time for the light to get to Earth. And if the star is far enough away, the light hasn't had time to get here. Okay, nice. But there were real scientific problems as well. If all mass and energy were concentrated at that point, the amount of energy would be too great to allow for atoms or even subatomic particles to form. The universe would be too hot for stuff. If it exploded, then such a central force would send out energy in a spherical wave. Energy evenly spread out, like the gum we use to blow bubbles. But we don't see a smooth universe. We see a chunky one. The energy did congeal into clumps of mass, stars, and galaxies with huge amounts of dead space in between. What would account for the clumpiness of our universe? How did we get the elements we have? How could atoms have formed and then collected into stars? This was the question that was investigated by George Gamow, the Russian-born American astrophysicist whose name is most closely associated with the Big Bang theory. In an important paper in 1948, Gamow and his graduate student Ralph Alpher proposed a mechanism for the formation of atoms in the period following the Big Bang. This paper, one of the most important in the history of cosmology, included as a co-author the physicist Hans Bethe. The truth is that Bethe had nothing to do with the research, but being an irrepressible punster, Gamow really wanted to have the authorship resemble the beginning of the Greek alphabet, and so the article is known today as the Alpher-Bethe-Gamow paper. One of the results of their work is a version of the bubblegum problem. Right? We have a clumpy, not a smooth universe. If there was really a compressed energy state, then an explosion or some outward pressure, right, there should be a uniform distribution of energy, not space and stars as we have it. They showed how the basic elements, hydrogen and helium, could form and how much of them we should find, but they also concluded that there should be some bubble gum left out there. That is, there should be energy remnants of the Big Bang spread evenly throughout space. It should be everywhere, and it should all be at the same decreasing energy. The reason it's decreasing is the same reason our bubblegum bubbles pop. Right? When you want to blow bubbles, right, you put gum in your mouth, right, 1 piece, 2 pieces, 3 pieces, you chew, and then you blow. The bubble gets bigger and bigger. As it gets bigger, the wall of the bubble gets thinner and thinner. Eventually, the air pressure from our blowing is greater than the strength of the wall, which is decreasing because it's getting thinner and thinner. When the wall can't hold it anymore, pop! We have to peel gum off our faces and out of our hair. After the Big Bang, there should be that original energy, but as it fills an increasingly expansive universe, it should be getting weaker and weaker because it's everywhere and there's more everywhere to fill. They calculated that it should be somewhere below 5 degrees above absolute zero, the coldest possible temperature. Unfortunately, at the time, no one could detect this. But it seemed pointless anyway. The theory seemed completely unscientific. If the universe is expanding and the two possibilities are constant expansion or Big Bang, we need to take the constant route seriously. After all, like Einstein, scientists dislike the idea that things aren't the same everywhere, and that there were unique events in the past that could not be recreated in the lab. But what then is causing the expansion, and why do we see galaxies? Where did they come from? Why don't they all die out? If the universe is getting bigger, then the energy density, the amount of stuff in any region, is getting smaller and smaller. This should mean the universe is dying. But that's not what we see when we look at the night sky. Any theory which would preserve a static universe while allowing for the expansion observed by Hubble would have to account for this fact: the apparent continuity of energy density in the universe. That is, the fact that the energy in any given region of the universe is not dropping off. Two astronomers, Thomas Gold and Hermann Bondi, escaped Nazi-occupied Austria during World War II. Fleeing to England, where they landed positions at Cambridge, they both worked on this question and often went to the movies together. One night, they went to see the British horror classic Dead of Night, with Mervyn Johns, Guji Withers, and Sir Michael Redgrave. He's really good in that. The film is set on a British estate, and a group of strangers are brought together. One of them, Walter, swears he's met all of them before in a recurring dream, and that the entire evening is a frightening case of déjà vu that will end with the breaking of one of the characters' glasses. Inspired by this statement, each recounts a different event in which they had to face the occult. In the end, the conversation climaxes with the breaking of the character's glasses and Walter awakening in a cold sweat. Walking home from the cinema that night, Gold and Bondi wondered if the universe could be self-creating in the same way that the film's plot was. Maybe the expansion allowed the universe to create itself by allowing for the spontaneous creation of bits of mass and energy. But this seemed problematic because one of the fundamental principles underlying the paradigm of modern physics is the conservation of energy. Energy is neither created nor destroyed. Where would this energy and mass magically come from? Their fellow astronomer and Big Bang opponent in Britain, Fred Hoyle, came up with an idea. Maybe it's not a violation of conservation laws, but the result of conservation laws. Maybe we could think of the Einsteinian static picture in terms of the conservation of energy density. Yes, the universe is expanding, but as it expands, there always has to be the same amount of stuff per unit volume. There's a field throughout space that itself stores energy. When the universal expansion drops the average amount of stuff in a region below some threshold, this energy storing field concentrates its energy and increases the mass and energy of that region. If this were true, then we would have conservation of energy and conservation of energy density. This was called the steady state theory, because it proposed that the universe was always in a constant state with respect to how much stuff per unit volume there is. So, the fight between Big Bang advocates and the steady state theorists was like a heavyweight prize fight. Plenty of passion and violence, but it stayed contained to the ring. The two camps attacked each other, but in the larger community, not many scientists paid much attention, because either way, the question seemed non-scientific. Except in New Jersey. At MIT and then Princeton from the 1940s to the 1960s, the physicist Robert Dicke was one of the world's experts in microwave detection. Now, if Gamma and Alpher's work was right, the detectable background radiation left over from the Big Bang would be in the microwave part of the electromagnetic spectrum. He would be the guy who could find it. So, he had built a sort of radiometer that was needed previously, but the one needed to detect Big Bang leftover radiation would be expensive and hard to build. No one outside of NASA could really afford such a project. But if Dickey could figure out exactly what it was he was looking for, and then create a strong enough radio telescope, then he could answer the question that Big Bang and steady state folks were arguing about. So, Dickey enlisted fellow physicist Jim Peebles to rederive gamma and alpha's results, only more exactly. And they figured out that the background radiation should be about 3 degrees above absolute zero. So, Dickey set off on the long process of creating the instrument to test the hypothesis. At the same time, right down the road from Princeton in Holmdel, New Jersey, take Route 33 and turn left on Route 4, at Bell Labs, Arno Penzias and Robert Wilson were using a radio telescope that NASA decided it no longer needed for communicating with weather satellites. They were going to use it for some radio astronomy. Other researchers had been analyzing the radio waves coming from the space containing the galaxies, but Penzias and Wilson wanted to look at the signal that came from between galaxies. These were going to be faint signals that required precision observation. They had their hands on a super-sensitive instrument, and so they wanted to do super-sensitive science. First, they needed to remove all the interference. Radio broadcasts, radar from the area needed to be screened out. This was long and exacting work, and through it all, there was this low hum in the background they could not seem to get rid of. They couldn't figure out where it was coming from. No matter where they pointed the antenna, they could not get rid of this background noise. They checked everything, multiple times, but still, the background static was there. Frustrated, they trotted over to Princeton and chatted with Jim Peebles. When he asked about the frequency of the noise, he had a sense of what it might be, and so he sent them to see Robert Dickey. Penzias and Wilson had accidentally found the signal that Dickey was working so hard to try to find. Gamma's background radiation had been discovered, and it was just what Dickey said it should be. The best explanation for it is that it's the leftover energy from the Big Bang. Here was empirical evidence. What had been the purview of religion or philosophy suddenly became science. Cosmology now gave rise to questions about the beginning of time. Did the universe have an origin? Will gravitation cause it to recollapse on itself in a big crunch? Or will it cause another Big Bang? Or is there not enough mass and energy? Will the universe expand to the point where the energy density is too low to support stars and galaxies? Is the universe doomed to a slow, cold death? These are now questions that are legitimately asked by scientists. Questions that for decades scientists thought were not even questions, since they assumed we lived in a stable, fixed universe. Cosmology, coming out of Einstein's general theory of relativity, gave rise to ideas that forced us to re-envision the universe in strange new ways. But this was nothing compared to the strangeness that emerged from another theory that scientists were forming at the time: quantum mechanics. That is weird.